Dear students, now we are going to discuss about concepts of controllability and observability. So the controllability and observability are two important properties of state model which are to be studied prior to the designing a controller. So the controllability deals with the possibility of forcing the system to a particular state by application of control input. The state is uncontrollable, then no input will be able to control the state. On the other hand, whether or not the initial states can be observed from the output is determined using observability property. So thus, if a state is not observable, then the controller will not be able to determine its behavior from the system output and hence not be able to use that state to stabilize the system. The next we are going to discuss definition of controllability. A system is said to be completely state controllable if it is possible to transfer the system state from any initial state to any other desired state in specified finite time by a control vector u of t. So the controllability of the state model can be tested by Kalman tests. So the Kalman methods of testing controllability is consider a system with state equation x is equal to ax plus bu for this system. A composite matrix QC can be formed such that QC is equal to BA square up to an power minus 1 B, where n is the order of the system. The next thing is, in this case, the system is completely state controllable if the rank of the composite matrix Q is the n. So the rank of the matrix is n if it is determinant of n into n composite matrix QC is non-zero. The determinant of QC is not equal to 0, then the rank of QC is n, so the system is completely state controllable. The next thing we are going to discuss of definition of observability. A system is said to be completely observable if every state x of t can be completely identified by measurements of the output y of t over a finite time interval. So for that, here also we are using Kalman methods for testing controllability. So consider a system with state model x is equal to ax plus bu and y is equal to cx plus du. For this system, a composite matrix Q naught can be formed such that Q naught is equal to Ct At Ct At square, like that up to n value it is extended. So where the n is the order of the system. If you define the say order of the system 2, then you can write the equation as Ct into Ct space At square Ct, like that. Okay. So now you have to remember this term Atn minus 1 into Ct. Atn minus 1 into Ct. If the n value is 1, so you need to write At power 0 Ct, like that. So in this case, the system is completely state observable if the rank of the composite matrix Q naught is n. The rank of the matrix is n, so the determinant of composite matrix is non-zero. So now the feedback control. The control system designed via pole placement by state feedback. So in the conventional approach to design a single input, single output control system, a controller or compensator is designed such that the domain closed loop poles have the desired damping ratio epsilon and the undamped natural frequency omega n. So in the compensated system, the output alone is used as feedback signal to achieve desired performance. In the state space design, any inner parameter or variable of the system can be used for feedback. The system state variables or parameters are used for feedback, then the system can be optimized for satisfying the desired performance index. So in the control system design, by pole placement or pole assignment technique, the state variables are used for feedback to achieve desired clock loop poles. The advantage in this system, the closed loop poles may be placed at any desired location by means of state feedback through the appropriate state feedback gain matrix. So the necessary and the sufficient condition to be satisfied by the system for arbitrary pole placement, the system to be completely state controllable. So consider the nth order SASO system with or without state variable feedback as shown below. So now see here. So this is the SASO system with and without feedback. So now here the feedback signal sigma is obtained by the state feedback and is related with state variable. The sigma is the kx, the k is the state variable feedback gain matrix, and the k value from k1 k2, the mu is the difference between system input and the feedback input.